first, I'd like to start by showing this wheel of misfortune, which sums up some of the tried designs for aerial vehicles that attempted to combine VTOL capability and efficient forward flights. And most of these designs have been canceled or failed. The ones in bold are the successful ones. And this is kind of an old chart. So actually, the blue ones, they were like the Lockheed Martin X-35B in competition with the Boeing X-32B. And the one that succeeded is the Lockheed Martin vehicle, which is now the F-35B, and which is one of the very rare successful examples of vehicles that are able to combine the advantages of fixed-wing aircraft while having this VTOL capability. And so why do we have such a low success rate? And why is it so hard to make vehicles that can take off and land vertically while being able to have large ranges, significant airspeed, like fixed-wing aircraft do? So starting with the basics, we can first look at momentum theory. And momentum theory tells us what is the ideal power required for a rotor to create a given thrust. So imagine on the left that this thing is an ideal rotor. So there is some free stream velocity upstream. So the air actually in hover would be the air would be static. So in hover, the upstream velocity of the air is 0. And it is accelerated via this perfect actuator disk. This air reaches an induced velocity VI at the actuator disk and ends up having downstream a final velocity that we can show is equal to 2 times VI. And so we can compute the power required to create a given thrust T based on the properties of this rotor. And the only relevant property for this rotor is this area A. Okay? Rho here is the air density, and T is the thrust. So usually we can define this dl value, which is the disk loading, equal to the thrust divided by the area of the rotor. And what we see from here is that the higher the disk loading is, the lower the required power to achieve a given thrust is. So a lower disk loading results in a more efficient rotor. And how to achieve a lower disk loading? By having a larger rotor. So this momentum theory tells us that if you want to achieve a given thrust very efficiently, we need a large rotor. So the question I ask is, does it mean we have to try to build the biggest rotors as possible for a given vehicle? So of course the answer is no, because there is like some constraints and issues that come up with a large rotor. And first of all, one of them is the fact that if we have a large rotor, we are going to need some added structural weight to even hold that rotor. For example, if we look at a helicopter usually has a tail rotor to create a counteracting torque that opposes the torque created by the main rotor. And to hold that tail rotor, we need a tail boom. And that tail boom needs to be big enough because we don't want the tail rotor to be under the main rotor. Otherwise, there's going to be some wake interference that will render the tail rotor ineffective. So a larger rotor means a larger tail boom, a heavier vehicle in the end. Same if we look at multi-rotor vehicles, we need some rotor arms to hold the rotors. And so the larger the rotors are, the heavier these arms will be. So we can wonder, OK, so larger rotors result in more weight. But can we quantify that? So the intuition would be to think that if we have a rotor of radius r, the added structural weight required for that rotor scales with r to the power of 3. Because if we scale everything the same way along each dimensions, then the weight scales proportionally to the volume, so to r to the power of 3. So, OK, we can assume that. And then it means that if we have a rotor and we want it to create a nominal thrust to hold the weight W, and then plus the structural weight incurred by the size of that rotor, it means that that rotor must be able to create a thrust equal to W plus alpha r to the power of 3, alpha being just some scalar coefficient. And so we can find the optimal size for that rotor by looking at the total power consumption. So this one comes from momentum theory that I just described. Okay? So we have the thrust to the power of 3 over 2 divided by, we have the square root of the area of the rotor, so we have r that ends up here. And so we find some optimal rotor radius that scales with the nominal weight we want to lift to the power of 1 over 3. Lower than that, and we lose in efficiency because we have a higher disk loading. Higher than that, and we lose in efficiency because the structural weight required for that rotor becomes too big. So here we see that that's the first example that tells us we don't want that rotor to be too big. But there is also a second way of looking at how the structural weight scales with the size of the rotor that is maybe more appropriate and is based on structural perspective. So instead of saying that the weight scales with the volume of the rotor, we might think, so if we hold a rotor, let's say, with a tail boom, and we increase the size of the rotor, we want to increase the size of the tail boom such that the overall stress in the material of the tail boom remains constant. So a local property that depends on what type of material. And so a simple example to see how that would work, we can imagine, so here I'm doing a little bit of structural mechanics. We have a cantilever beam that you can see here. And we imagine we have a prescribed length. And we ask the question, what is the radius that we want so that we maintain the stress at the maximum stress in that beam under its own weight at a given level, okay, as a function of the length of the beam. So we can use Euler-Bernoulli beam theory to do that. And what we find out is that if we look at the stress, which is given by the moment times the radius divided by the second moment of area of that cross-section, we find that the rotor, the radius of that cylinder must scale with its length to the power of 5. So that's even worse. If we double the length of that cylinder and we want the stresses in the material to remain the same, we have to multiply the radius by 16 or 32, 2 to the power of 5. So that's a lot. That's a lot of added weight. And if we do the same kind of analysis and we look at what is the optimal radius for a rotor, imagining that the structural weight that is induced by the rotor radius scales with the radius to the power of 5, we find some optimal rotor, unsurprisingly, that depends on the nominal weight to the power of 1 over 5. So we have like two different ways of maybe trying to have a guess of what is the ideal size of a rotor, the ideal size of a rotor, yes, to lift a certain weight. In one of the first example, we had a cubic dependency. Here we have a dependency 1 over 5. But in general, if we assume that we have some sort of dependency, which can be actually verified by data, so here we have in this paper, it's actually in the book by Leishman, this book, Helicopter Sizing by Statistics, the author looked at many different types of helicopters ranging in weight and looked at the rotor size and show a good correlation between the radius of the rotor and the weight of the helicopter to the power of here 0.308. So it's something in between, if we look at the weight as dependency of the radius, something between r to the power of 3 and r to the power of 5, closer to r to the power of 3. Potentially because the example of the cantilever beam is not the most efficient structure to sustain its own weight. So if we look at a more efficient structure, it would have to something less than r to the power of 5. But in any case, there is some dependency that is shown in data on existing helicopters. That therefore must be guided by some inherent physics principles regarding the design of helicopters. And so if we assume that we have some dependency where we have the optimal radius to lift a certain weight that depends, that has this dependency on the weight. And here we say to the power of 1 over gamma, gamma being some arbitrary scalar that is, in this case, more than 2, which means that as we add in the radius, the available thrust that scales to the square of the radius will scale slower than the actual weight that we need to support that rotor. So if we assume this kind of dependency, we can find out the optimal radius for a given weight. We can look at the thrust of that rotor given by momentum theory and the power induced by that rotor. And these coefficients don't matter. It's just scalar coefficient. What matters is this dependency. And what it means, this dependency, is that this function p, the power with respect to the weight that we want to lift, is convex. Okay, because here gamma is greater than 2, so the power over here is greater than 1. So we have a convex dependency between the ideal power to lift a given weight W. And because of that, it may be more advantageous to actually use multiple smaller rotors rather than one big rotor because of this convex dependency. If we look at the power required to lift a given weight W with a rotor of optimal radius accounting for the added weight that is strictly dependent on that radius, well, that power is higher than if we have n optimal rotors, each lifting W divided by n kilograms. So this relationship tells us that there may be cases where we want to have more rotors than more small rotors rather than one big rotor. And we also see that actually the disk area is also smaller in the case of many small rotors, which means that we have a higher disk loading but a better power consumption. And so why should it always, well, why is it not, what are reasons for it not to be always true? If we look at the Reynolds number, which are lower for small rotors, there will be more viscous effect and more losses at the rotor for small rotors, okay? So this conclusion that I got from momentum theory and by considering the added weight that comes with a larger rotor will not be true for every possible rotor size. And in general, there are many other factors to take into account. So for example, maybe that using smaller rotors means that is actually more weight required when comparing just to one rotor in terms of the weight dependency with the size of the rotor, because we have to somehow like assemble these multiple rotors together. So there are like some possible elements that make think that maybe it's not always true, but however, it could be that there are some cases where more rotors are better than one rotor, and I will come back to it and give you some practical examples of where that could be the case. But before that, I want to mention forward flight, because at the beginning I said there was some trade-off between having an efficient rotor at hovering and an efficient rotor in forward flight. So if we look again at the power consumption resulting from momentum theory as a function of velocity for a rotorcraft in horizontal flight, we see actually that the power consumption decreases and reaches a minimum before increasing again. And it is well known that helicopters or multi-rotor vehicles have a greater endurance when they are moving forward rather than staying at a hover. And so we can see that by momentum theory. And if we look then at the range at a given velocity, which is related to how much energy is required to go a certain distance at a given velocity, so that's the plot on the right, well, there is a maximum that is at a certain velocity, okay? So which means that if we want to design a vehicle which mostly will fly in horizontal flights, and we want it to fly at a certain velocity, ideally we want that peak right here to be at that given velocity so that we have the greater range. And now is the question, what happens if we actually compare different disk loadings regarding that power efficiency? So here, I take the examples of like a same vehicle, so same parameters, only the disk loading changes by changing the rotor area. So if we increase the rotor area, which corresponds to the first case, we have, unsurprisingly, sorry, I said increase the rotor area, so we have a lower disk loading, which corresponds to the last case, and we have a lower power consumption, okay? And so we have also a higher range. But the difference at high velocities don't really are small compared to the overall range. And same if we look at the power consumption, the differences between disk loadings are small. So here we have like a disk loading that's twice as much as the last one, but the differences in power consumption at high velocity don't matter much. And because of and with the higher disk loading, we have a much smaller rotor. It might be preferable to use that smaller rotor and have maybe a slightly higher power consumption, but in a much smaller profile. So there are like design criteria like this. So in forward flight, if we do mostly forward flight, maybe there is like an advantage in using higher disk loading for a smaller vehicle, even if the power consumption is slightly higher, because overall that relative difference is small compared to the total power consumption. And there are other reasons actually that support this. So I just mentioned small relative improvement from large rotors by using smaller rotors with a higher disk loading. There are other aspects of forward flight that favor a smaller disk loading. Mostly issues related with retreating blade stall and reverse flow, which happens when the velocity of the retreating of the air relative to the retreating blade becomes so small that it can incur blade stall, or even being negative velocity, incurring negative lift. So that's something that's absolutely undesirable, and having a higher rotor velocity, which correlates with higher disk loading, is preferable. Also, if we look at the actual versus ideal performance, ideal being the one given by momentum theory, we see that from this plot that for higher disk loadings, which correlates with higher thrust coefficients, the actual performance is closer to the ideal one, and that is measured by the figure of merit. The figure of merit being defined as the ratio of actual rotor performance versus ideal performance. So higher disk loading, the actual performance is closer to the ideal one, so that might be preferable as well. And this is an example of a helicopter with a very high disk loading compared to other helicopters of that same class, so the RAH-66 Comanche, which was only a prototype and was cancelled. And why this helicopter has such a disk loading? Because it was meant for reconnaissance and attack helicopter and needed to have a high forward velocity. So this design criteria regarding rotor size and disk loading depend on the applications. If we design a vehicle that is mostly meant for hovering, it is preferable to have larger rotor and small disk loading, but for forward flights, it is preferable to have, in general, a higher disk loading. And so we also have seen that larger rotors can be advantageous because of the weight incurred by one rotor versus multiple rotors. And we can see that with examples of recent developments in distributed electric propulsions. Before electric propulsion, it was harder to actually have many small rotors rather than one big one, because gas turbines tend to be more efficient as they're bigger, which is not the case for electric propulsion. So the fact that we can use electric motors enables this possibility of using many rotors rather than one. And there are other obvious advantages, which are redundancy, lower noise. And also, I'd like to mention an important one, I think, is just the economies of scale by having many small rotors perhaps used on different types of vehicle rather than each vehicle having their own rotor. And you can see actually on these three different, well, there's actually two different prototypes here. By wing, they actually have the same rotors, same propellers, so exact same components for the propulsion. The only thing that changes is how many of them there are to adapt to a given payload weight. And in fact, if we look at other rotorcraft that are used for diverse applications over a wide range of maximum takeoff mass, we see really that the flight time doesn't correlate that much with the maximum takeoff mass. So bigger vehicles with overall bigger disk area don't really tend to be much more endurant than smaller vehicles. Other design criteria are much more important. For example, what is the weight percentage of the vehicle that is allocated to batteries. So all of them, actually, of this one are battery powered. And we can see that maybe the smaller ones have a less flight time, but from some, after a certain point, there's not much difference, or at least no correlation between size and flight time. Okay, so for various reasons, I made the case that it is possible that for some situations, it is better to have a vehicle with many small rotors rather than one big rotor. And I'd like to take it a step further by saying that if we have a vehicle with many small rotors, we might as well split up these rotors in different modules to create vehicles which are modular and reconfigurable. And why do we want to do that? For example, because these vehicles would be easier to store. They can be broken down in different parts, which is more convenient for storage and transportation. We can also optimize the disk loading or even the configuration of the vehicle we use, given a task and a payload. We also have more redundancy, not only on the propulsion system, but if like all the modules are like self-contained, the energy distribution, the flight control can be distributed, and hopefully this can lead to a safer system. By only using the number of modules appropriate to a task, it would be possible to have a higher rate of utilization of a given fleet and overall a higher versatility. And modular reconfigurable vehicles are what I worked during my PhD thesis. They're not a new concept, so they were proposed already, as you can see, a few years ago, even before that. But I like this work because it sums up some of the advantages. So this is a work by Boeing, which is called the LEAF project. They had this working prototype. So here it's actually 4 quadcopters that are linked together and carry together a weight. And they argued, just like I did, that it could be more convenient for some applications because you can separate the different modules, put them in a truck, then go to a site where you need to do some work with these modules, assemble them, and lift some heavy weight. And here their concept was actually tethered. So it was for like moving stuff on construction sites where the radius is limited, the radius where the vehicle needs to operate. But there are also other works, of course. So like one of the first ones was the distributed flight array at ETH. This one is the one I just mentioned, the LEAF project. And more recently, there is ModQuad, which is a project at UPenn. So they're all kind of different. In this one, the particularity is that one module cannot sustain flight by itself because there's only one rotor, so it is underactuated, and they need like four modules to be assembled together to create a controllable aerial vehicle. And the particularity is also that these modules can move on the ground to self-assemble. ModQuad uses quadcopters as modules, so each module is itself an aerial vehicle, and the particularity is that they are able to self-assemble. They have magnets to create modular vehicles of different sizes. But there's one main limitation with this type of design, is the fact that modules assemble in a plane. And I mentioned before, okay, so if we want, if maybe there is a structural advantage in using many rotors rather than one because we have lower structural weight, but might not be the case if we assemble all the rotors in a plane, especially if it's for carrying some payload. If we imagine that we scale up the number of modules and we scale up proportionally a force that is applied to them, where we imagine that we have some payload that is lifted by some flight array, then the amount of bending will increase with the number of modules, and that bending can lead to several issues. A loss of efficiency, because now all the rotors are not all parallel, increased stresses that can lead to structural failure, and overall, even just the fact that the structure is less stiff can make it harder to control. And a second limitation of planar assembly is the fact that we may also want to have the possibilities of creating 6 degrees of freedom vehicles. And I will show you how after, but that's not possible with planar assemblies. Because the way to do that, well, there are two ways to create 6 degrees of freedom vehicles. The first way is to have tilting rotors so that the thrust that is generated by the vehicle can be vectored. When I say 6 degrees of freedom, I mean that it is possible to independently output a 3-dimensional torque and a 3-dimensional thrust on the airframe. Okay, so if you can tilt the propellers, it's possible. Or if you have at least 6 propellers with different tilt angles, it might also be possible to have 6 degrees of freedom, like on the Omnicopter that you can see at the bottom right. This one uses tilting propellers. And why do we want to do that? Because if we want to create a versatile system, modular system, 6 degrees of freedom opens new applications, mostly related to aerial manipulation. If we imagine that a modular, well, an aerial vehicle is used for aerial manipulation, for example, as you can see here, for probing some surface or like for holding some robotic arm, we would want this vehicle to be able to compensate for arbitrary moments and forces, hence the need for a 6 degree of freedom vehicle. We cannot do that with planar assemblies, but we can do that with some types of modular vehicle. Not the first one I present, though. The first type of modular vehicle I present only tries to answer the structural limitation issues, and it's based on a fractal shape. So imagine that one module has this tetrahedron shape, and that successive configurations, larger and larger, of modules are assembled by creating bigger tetrahedrons from this fractal shape, which is called the Sierpinski tetrahedron. Then there are two things that are important with this type of configuration. The first one you see on the right is that there is no rotor overlap at any iteration of this fractal shape. So we minimize the loss of efficiency that would happen if there was two rotor overlapping. And the other thing is that this structure has proportions equal in all 3 dimensions. So it is fair to assume that it is more rigid than a flat configuration. And we can prove that later on. But this shape has these two advantages. So rigidity in 3 dimensions and no overlap. It's actually not a novel concept because Alexander Graham Bell basically did the same thing more than a century ago with kites. And the reason he gives in his patent are exactly the same as I just mentioned. Structural rigidity and unobstructed airflow throughout that kite. And so he built several iterations, flew them, and we try to do the same, but with actuated vehicles. So we built this first prototype. The modules are not self-contained. Actually, it's more like just one monolithic quadcopter vehicles, except that the propellers follow the shape of a tetrahedron. What we wanted to verify is that we would be able to fly it. And we encountered some issues, mostly related to yaw control authority. And I will not really get into details of what, but it's not unsurmountable. This issue was mostly related with the resulting control allocation matrix that comes from this specific configuration, where one of the rotor, the top one, has to work three times as much as the other rotors to be able to control yaw, and as a consequence easily reaches saturation, which is an issue for yaw control authority. But we still threw it, and there was another iteration of the prototype that was built that was lighter and more efficient, that didn't have this issue. Because there was more leeway in the input of the rotors that was available before actuation saturation is reached. So here you have a first iteration, 4 rotors, and the second iterations here with 16 rotors. But so I mentioned this, also the fact that we may want some 6 degrees of freedom vehicles, and we cannot do that with this tetrahedron shape, or at least not easily, and maybe certainly not efficiently. So what I tried to do next is come up with a different type of modular vehicle where we could also build some 3-dimensional assemblies in order to have good structural properties, but also being able to orient the different propellers in different directions, such as 6 degrees of freedom vehicles can be constructed with this module. And so that's the next module basically came up with. So it's the shape is the one of a regular dodecahedron. So it's just one of the 5 convex polyhedra. And the idea is that because of the symmetries of the dodecahedron, we can change the orientations of the propeller in a rigid vehicle. So it's more like when the vehicle is assembled that the orientation of the propeller is decided. But there are more possibilities, therefore allowing 6 degrees of freedom vehicles. And the connection mechanism between 2 modules is the one you can see here. So it's not very intuitive, actually, because you have like two dodecahedra. You take 2 vertices on the same face on each, which are not next to each other. And you basically connect these 2 vertices, and so we can see that the faces do not coincide. And so I'm often asked, so why not just connecting 2 faces together at the 5 vertices? And the reason is that if we do that, we won't be able to connect a 3rd module to both of the first 2 modules, because the angle that is formed, the dihedral angle of the regular dodecahedron, which is the angle between 2 faces, would have to be 120 degrees to do that, and it's not the case. It's actually lower than that. But with this connection mechanism, we can actually connect a 3rd module, let's say on top, that will be connected to the 2 other modules. And so we have basically a triangle made of dodecahedra, if that makes sense. And so we can actually create more structurally efficient structures and recreate a lot of existing rotorcraft configuration. And also, if we restrict the number of connections by using only some subset of vertices, we can show that by considering the successive translations incurred by these connections, we have a lattice of possible connection positions, which will be useful for optimizing over the feasible configurations. And so you can see here, by using these connections, we can recreate standard configurations. So it might be a little hard to see, but here we have 4 modules forming a quadcopter. Here you have a hexacopter, here an octocopter, so with 8 modules. And the color is supposed to represent whether the rotors are rotating clockwise or counterclockwise. But we can also recreate tetrahedron configurations. So we can create a basic tetrahedron and then apply the same fractal tetrahedron rule to create successive iterations of bigger and bigger tetrahedron. And by changing the orientation of the propellers as the modules are assembled, we can also create some 6 degrees of freedom configurations. I mentioned configuration optimization. So with this type of connections between modules, there is like a vast set of feasible configurations. And I mentioned the fact that we may want some modular vehicles so that we can adapt the number of modules to reach a specific disk loading, or like to lift a certain payload. So the question is, how do we actually optimize over the space of configurations to reach some optimal given given a task. So let's say lift a certain weight. And there are several things that are of interest that we want to optimize over, either as performance to optimize or like as constraints. And so we can consider dynamical properties, mostly control authority or the degrees of freedom of resulting configurations, but structural properties as well, because we want the structure to be able to hold its own weight. But also we want to look at power consumption, range, and eventually shape. That might be a criteria, having like a smaller profile for a vehicle. So starting with control allocation or control authority, I'm not getting into the details because I don't have time, but for a given fixed configuration, we can formulate control allocation problems with a static matrix, which means we're trying to find a matrix which is a pseudo-inverse of another matrix given by the position and orientation of the rotors on a fixed configuration. And so we can formulate this problem where control allocation matrix, if we have an over-actuated vehicle, there's an infinite number of them. And we want to find the optimal one given some criteria. And if we look at average power consumption, finding the optimal control allocation matrix results in a convex problem. What it means, well, because it's a convex problem, any local minimum is a global minimum, and that makes it easier to find it in practice. We have the same thing if we look at the average power consumption per module rather than at the vehicle scale. And if we look at the control allocation matrix, that will minimize some measure of control authority along some control axis. So it can be, for example, like the 3-degree moments that can be output, or like the 3-degree thrust that can be output by a 6-degree of freedom configuration. We end up with a second-order cone problem, which is a subset of convex problems, which is, in fact, much easier to solve than convex problems. And so that is for a fixed configuration. But because we have this, we can later on incorporate them in optimization over variable configurations, which will still result in problems with sort of a nice structure. So here, just an example, like if we consider this 6-degree of freedom 12 rotor vehicle, and we want to find the control allocation matrix that maximizes the available moments along the 3 axis. We have, as I mentioned, a second-order cone program. We can solve it, and we end up with this kind of this shape for all the moments available, which is better than if we use the more Penrose pseudo-inverse, which is the standard way usually of finding a control allocation matrix. So it might not be obvious from the shape, but here you have like the radius of the inscribed spheres, so the biggest sphere you can fit in this set, and we see that this one is about, I think, 25% bigger than this one. Now I mentioned also structural properties. So how do we deal with optimization over the structural aspects for these configurations? Well, we can represent this as frame structures. So each of the bars that are used to create these modules are actually beams. And by using some elastic stiffness hypothesis, the relationship between external forces and displacements of this frame is linear. So if we apply some forces, we can find the displacements by using the inverse of that stiffness matrix. What matters here is that the relationship is linear, so that will be convenient when we want to use this relationship in optimization programs. I mentioned the fact that the feasible positions form a lattice. So what we can do is we can consider a subset of all feasible positions and orientations of the modules and describe it with integers. And that means that if we want to optimize for a given, an arbitrary configuration, and let's say optimize over like the stiffer configuration with some constraints maybe on the achievable thrust and moments, that we end up with a mixed integer convex program. A mixed integer convex program is a program where we start with a convex program, and then we have some variables that are actually integers. So it's not convex anymore, but there are still methods to solve this program pretty efficiently depending on the structure of the program. Still not as efficiently as convex program, but not bad at all. So we can formulate this problem, for example, like finding a 6-degree of freedom 12 module configuration which maximizes yaw authority. That's a mixed integer, some second-order cone program, and we end up with this configuration. If we formulate a simple program of finding a 4 degree of freedom 4-module configuration, and well, which maximize some structural performance criterion, we end up with this tetrahedron structure. All right, now let's talk about the prototype. So that's the module we built based on this dodecahedron shape. As you can see, here we have like the corners where the connection between the modules happens. And we recreated different configurations. So here we have the quadcopter. Here we had the hexacopter. We also built some tetrahedron quadcopter, and that's the biggest one we've built with 16 modules. So 4 tetrahedra, each one of them being made of 4 modules. We had a couple of flights that were performed. So here we see like the quadcopter version. Here that was just a hexacopter flight with one of the rotor that was disabled. So it's actually a non-standard hexarotor configuration. And we also flew a little less successfully the non-conventional configurations. They're actually much harder to control. For the tetrahedron configuration, the main issue is actually there is some wake interaction with this module shape. And so it makes it just more challenging to stabilize it. At least we didn't like, we use like off-the-shelf flight controllers for that. And the overall tuning has to be done manually, and that was a very challenging process for these configurations. And this one, well, I don't know if we can talk about control flight, but it can lift its weight. But as you notice, the angle of the propeller is actually quite high. It's about 15 degrees, which means, well, actually, no, it's more than 15 degrees. I think it's a little more than 20 degrees. But the fact is, there is a significant decrease in overall thrust available. And because the modules themselves are quite heavy, we barely have any margin for controlling the vehicle. So that's why it was actually very hard to have a successful flight with this configuration. So to summarize, I started by talking about momentum theory, and I said, well, there are some cases where we may want to have vehicles with multiple rotors rather than one big rotor in terms of power efficiency. And that led me to then discuss what are the new applications that are open if we decide to completely separate these rotors in separate modules and introduce this work. So we create this three-dimensional vehicles, to have stiffer and better vehicles with better structural properties. And also mention how we can optimize over the space of feasible configuration with mixed integer programming. And I presented some of the prototypes that we have built. So from now, I thank you for your attention, and I'll take any questions. Yep.
Okay, I have a couple of questions, so maybe I'll ask one and maybe we can come back to me if there's time. So one of the questions, okay, thank you. So one of the questions I'm interested in is when you're doing the configuration optimization problem, did you constrain the possible direction of the thrust based on geometry, or did you actually do a search in an SO3 of the possible thrust directions for each module of the configuration?
So yes, I constrained. So I set actually the nominal control vector to achieve hover. So, and I set it like so that every rotor has the same control input for achieving the equilibrium at hovering, which makes sense because you probably don't want to have like different control inputs at hovering, because then the difference in power consumption would be too big. So that's the first constraint. And then I constrained the overall thrust vector at that equilibrium to be vertical and equal to the overall weight of the vehicle.
Okay, quick follow-up question. Like for each rotor within the within like one of the modules, did you constrain the possible directions for the rotor to be tilting at? Like, because I remember in your slides, you demonstrated different modules with rotors of different feasible directions within this single geometry.
Yes, so there's a finite number of directions these modules can take because they correspond to the symmetries of the dodecahedron. So I represented them with integer variables. And in fact, I didn't even consider all orientations because I ruled out like directions that result in a negative thrust because it wouldn't make sense to have that. So in fact, there's only like I only consider like a rotor pointing up, or like 3 possible directions for the rotor being tilted. So yeah, there's like 4 possible directions of the rotor, and also 2 possible rotation direction of the propeller.
Thanks for your great talk. My question may be more related to the application field. I saw the flight array image that there is one image with like multiple UAV connected by the cubic frame. So I'm wondering if you have considering use such a design in the existing the unmanned aerial vehicle cargo delivery program, because I feel like currently the way that researchers use the UAV to solve the last mile problem, they are mostly consider the specific design of the drone with the specific limitation of the weight of the delivery. And I feel like your design is kind of very ideal way. It can be implemented to such a service very ideally. So I'm wondering what's your insight about the application field of your design?
Yeah, well, thank you for the question. So yes, I think there could be applications, as you mentioned, for cargo delivery. Mostly when there is a need to transport very diverse cargoes, because that's the advantage of being able to increase the payload capacity. If you know that you're going to be carrying things, for example, like under like 5 pounds, like for consumer delivery, it's probably better to have just one purpose-built vehicle that can do everything from 0 to 5 pounds. But let's say that you may want to transport things from like 10 to 100 pounds. It would maybe makes more sense cost-wise to have such a system, but then it also depends on the range, because this thing is this prototype. I mean, this whole concept is based on a rotorcraft vehicle, which, I mean, when you have like with parallel rotors, but which is less efficient than a fixed-wing aircraft in terms of range. So I think it would be relevant if for like short distance, like payload agnostic deliveries, and that's why I think there is there is definitely a possibility for something like that. And I was really happy when I saw the picture of the as I showed the alphabet fleet, the wing, the different wing aircraft that use all the same motors. Because it's exactly what I'm saying. It's like it's maybe like it costs less money to just have the same types of motors and the same types of propeller, and just add more of them on your vehicle depending on the payload. But if you can have everything modular, then you can even fine-tune better the number of rotors given the payload. Yeah, but yeah. So I think it would be the applications would probably be more for heavier payloads than what is typically the case with consumer delivery. And also if there is a need for transporting the vehicle, and that the ability to break it down in several parts is important. So, yeah. Yes?
Yes, I was thinking of the rotor of a turbine, then the blades of the turbine will be of controllable and different pitch, which will provide which will provide direction of travel.
You mean the impact of the turbine with the direction of travel?
Yeah, but the pitch of the blades on the turbine will control the direction in which the aircraft will go.
So I mean, I'm not sure how is that.
You have controllable pitch. You have adjustable pitch on the blades of the turbine.
If I have a picture, are you talking about this picture? Oh, no, don't see it. Okay. This helicopter with a turbine?
Well, if you have a turbine,
Yes.
you have the blades of a turbine on the peripheral circumference, and where, depending on where the blade is on the turbine, it has a certain pitch or a certain angle. The blade will have a certain angle.
Yes. So actually, yeah. In forward flight, one of the important design considerations is the tilt of the rotor with respect to the helicopter. So it makes sense. It's yep.
Not all of the blades have the same tilt. It depends on the tilt depends on where you are on the.
Yeah. Also, like so, if you look at is that something I didn't mention? Is the pitch of the blades on a rotor, yeah. and it's so that's one design consideration where the overall pitch and also the twisting of the pitch along the blade plays a role. And for example, it can be shown that at hover, a twisting that is hyperbolic, that is, we have the pitch time the distance to the hub of along the blade is constant, is the optimal in terms of power consumption at hover. But this type of hyperbolic pitching or twisting of the blade is actually seldom used in practice because it's hard to manufacture, and also because it reduces the overall efficiency in horizontal flight. So it kind of shows like another like design choice that results in a trade-off between efficiency in hover and in forward flight. Yeah, thank you for your question.
Let's have your last question, and then we're running low on time.
So regarding like when you said like one of the main application you consider is like for heavier payload, like moving heavier payload, then my question is, so there are some folks working on like multi-drone based payload control, but these drones are like not attached to each other.
Drone swarms.
Yeah, like swarms or like yeah, and like I'm wondering what is the main benefit of like having the drone all attached to each other, like compared to this like each individual drone like having their own like freedom, and then like some strings attached to the payload, so they move this payload together.
Yeah.
So because I think the latter, like for each drone, they have more like control authority. So there might be, in terms of like controls, like there might be more degree of freedom you can do, like to have some more like better maneuver of the payload or something like that. But yeah, here I was curious, like what do you think is the main benefit of? Like,
I mean that's a great point. You're right. There's definitely also the option of using drone swarms, and so some of maybe the advantages of using a rigidly connected vehicle rather than a drone swarm is that, so first of all, the control problem of a drone swarm is not trivial. It is much easier with a rigid vehicle. If you have a drone swarm, well, you want them to be able to cooperate. each vehicle, whether if they're physically connected and you have physical connections and data transmission, you can actually do all of that. You can also share power between the different modules. And just the fact that you want, like in a drone swarm, like every vehicle to have the right amount of tension to lift equally the vehicle is harder to achieve, and so probably will result in a higher overall power consumption. And the rigidly connected vehicle is also less likely to fail altogether. Whether if you have a drone swarm and one of the modules fails, well, I mean, maybe it's not a problem to lift whatever you're lifting, but the consequences are not the same if you have like one of the vehicles falling down rather than one of the modules in a multi-module vehicle failing. So that's, I think, the main differences. But I mean, I think both of them like are valid applications or are relevant in some ways. Thank you.
Thank you very much for coming.
Yeah, thank you, Helen.
Such as
Oh.
usually somebody much more important to me would give you this, but
Okay.
they are not here today.
Thank you very much.
Thank
All
you.
right.